And I share the screen. And I close the window. Okay, so it's the sixth talk where we'll be discussing convergence of a perturbation by a single grain. So let me recall. So we are dealing with a convex enclosed subset of R2 with non-empty interior, and A omega is the set of monomials, if you like, tropical monomials, which have non-infinite infimum. And omega is admissible if and only if this set of tropical monomials powers is not identically just 0, 0. So there is something. And I recall...
Jota, a little remark is that you didn't say it, but it's obvious that it's true. All the time you're supposing 0, 0 is in omega.
Yes. I told about this last time, but yeah. Anyway, it's indeed always there. So admissible means it's larger than a one element set. A omega is larger than one element.
Oh, yeah.
So and then if it's admissible, we can cook up the most useful, in a sense, tropical series, which is just the infimum of all support functions. So it's an infimum of all non-zero elements of A omega, and we add the AV, which is the minus infimum, so that the result AV plus Z times V is positive on omega. Okay, so sometimes we call this tropical normalized distance function to the boundary of omega. In a sense, it measures distance from the point inside to the boundary, and since it vanishes on the boundary, but yeah, I'm not sure it's the best way to call it. Anyway, so F omega is the tropical series which defines the caustic curve that we were discussing last time. And now that's the setup for what we are doing. We are taking a point in the interior and some h greater than 0, supposedly it's small, and this is going to be the step of the lattice, so that we can take discretization of omega h, which is the intersection of the interior of the omega with the h times z square, so the lattice with step h, and we take a p h in omega h, some rounding of p with respect to this lattice. So it might be that, for example, there is a single closest point from the lattice, but it might happen that there are 2 or maybe even 4. So we choose some of them, some of the closest points in the lattice to P, and call it pH. And now we consider...
I have a little question here.
Yeah.
This, if you go back one slide and you have this function that is that defines the caustic curve.
Yeah.
It also defines some, of course, in the complement of the graph of the curve. You have these chambers.
Yes.
You have these polygons or these chambers. And so what all the interior points on a chamber share a condition, and it should be very obvious. What is this condition that all the points in a chamber share?
That there is a single support function which takes the infimum, that F omega is linear with a precise gradient. And
it's linear with a precise gradient, and that in a way that the distance function is continuous on that chamber.
Yes, it's continuous globally, but it's linear on every chamber.
Well, I mean, it's linear. Sorry, it's linear in a chamber. The distance function is linear, and then there is an abrupt change, and the distance changes suddenly, or
it doesn't change chamber. The gradient changes suddenly. So if you cross from one chamber to another,
the gradient, yeah, sorry.
Yeah, so you just change the
is what?
The closest support function. So support the support line. So every chamber is the interior points of the chamber is the ones which have a single support line which is closest to them in this SL2Z invariant sense. And the distance is calculated as this.
Yeah. Even in the very different Euclidean distance, if I had a square or whatever, a polygon, even in the very different Euclidean distance, something like this would be happening, wouldn't it?
Yes.
If I had a point, there would be.
Yeah. And I find it. I think
that this is
we never thought about this seriously, but it could be a nice question to discover, like what happens on the SO2 invariant side of the picture. So many things can be repeated, and here the structure group, or like the symmetry group of everything, is SL2Z, and this gives tropical geometry, but we can try to do the same things in the Euclidean geometry. And yeah, it can be really interesting.
Fantastic. Thank you.
Okay, so now let's go back to the setup. We take the state, which is the perturbation of all three, like positive perturbation at this point pH. So we add a single grain to the all three state somewhere near P. And we call this state phi H. And the purpose of today's talk would be to study how the relaxation of this state looks like. So in a sense, we are probing the maximally stable state on the domain, and we want to relate the result to the geometry of the domain. And here comes the first theorem. So first of all, like the claim, this relaxation of this phi H will be almost everywhere 3. So if H is small, phi H circle is almost everywhere 3. So we are interested in the locus where it's not all 3. Let me even improve it slightly, because later we will use this for non-stable states. Yes. So the deviation locus is where it's less than 3. And for stable states, it means that it's 0, 1, or 2. And so the claim is that these deviation sets, when H goes to 0, converge to the tropical curve, which is given by the truncation of the previous tropical series. So you introduce the 0 term. So recall that in 2 slides back, this was exactly the monomial which was omitted. We didn't have the constant term, and now we are introducing the constant term, meaning that we truncate this pyramid so that this function is not smooth exactly at P. Okay, and so that's the first theorem, that the deviation loci converge to the omega tropical curve given by this deformation, if you like, of the caustic curve. Deformation by introducing the constant term. And here, like I need to tell these technicalities that this H on K convergence, so Hausdorff on compacts, means precisely what's below on this slide. So for any compact in the interior, and this is important that it's in the interior, it doesn't touch the boundary. And for any epsilon, there is some H0 such that for all H smaller than H0, the distance from the intersection of this tropical curve with the compact is less than epsilon from the intersection of this compact with the deviation locus. Okay, so that's the precise formulation of the theorem, and in this formulation, we didn't care what takes place near the boundary. So near the boundary, usually, if you consider the honest limit without these compacts in the interior, you also have some noise near the boundary. Okay, so that's the first formulation. Then there is something better. So you see here, we recover this tropical curve as a set. So I mean, this Hausdorff convergence, you don't recover multiplicities. You don't see multiplicities. You see just the set. And so to amend this, there is quantitative deviation that we never called like that before. But since that set was deviation locus, I say like why not call what really measures how much it deviates quantitative deviation. So, and this is the rescaling by h-1 of the difference of the state with the state 3. And what you see inside the brackets is just the way to extend a discrete function, a function on the lattice, to the function defined on the continuous domain. Okay, and so that's another formulation that the functions which are this tilde of the relaxation of the previous state star weak converge as h all goes to 0 to the distribution supported on the previous tropical curve. So let me say here again we actually need to tell that it's on the interior, so that for any test function the integral of the limit of the integral of the product of this tilde, this quantitative deviation with phi, is the integral over the tropical curve, where you actually recover the multiplicities. So multiple edges would have multiplicities, and also there is this weight that we encountered before, this prim of the E. Remember, we had this p square plus q square, and when we were talking about symplectic area. So this is where it reappears. It reappears as the weight in the limit of these integrals over edges. And yeah, so that's the theorem B. And finally, I find the most elegant, because we don't care about these boundary restrictions, is the following form for toppling functions. So recall that for a state phi on the discrete domain, we denote by h index phi its toppling function, so that it's the function which counts the number of topplings at every vertex during the relaxation of phi. And here, so the scaling limit of these toppling functions is just that tropical series, that distance with constant term introduced. So this is the constant term which I'm.
Theorem C implies theorem B.
It's more convoluted, so I would love to say yes, but actually the correct answer again that you prove C and then you realize that you can do some extra twists to prove A and B. So actually B is quite easy. So from what I'll tell you, you'll see that it's quite transparent. So you need to know.
In many ways, B is a very weak form of convergence, and as you said, theorem C feels more definitive. You know, theorem C feels like having more information.
Yes. So, for example, yeah. So
it's a bit surprising that you have to work harder to prove theorem B than to prove theorem C.
Yes. Well, you'll see that the proof of theorem C, the idea of the proof is quite transparent, and but you need to perform some extra work, and just theorem C wouldn't be enough to prove A and B. At least we don't know. You would really need to go deeper in understanding the proof, like what happens to deduce A and B. And so to announce today, we will mostly understand C, and I'll explain one step to understanding A. And in the talk which follows, not next time, but the time after the next, we will throw on a little bit more technicalities, and we will briefly repeat what I'm telling now, but mostly we'll be dealing with multiple points perturbation, so not a single point, but many, and also a little bit more of technical steps in establishing A and B. So today I'll be proving C and some easy implication towards A. Okay, so here is the plan. The strategy for proving theorem C. And actually this plan is quite detailed, so you don't need much more than that. So first you construct an upper bound on the toppling function. And this upper bound is very easy. You basically do the discretization of the limiting tropical polynomial, tropical series. So you just take this tropical series and you say, okay, it's not linear at point P. Therefore, its discretization has strictly negative Laplacian at pH. So adding this Laplacian of this discretization to the state phi h would result in a state which is less than 3. So here. And remember, we can use this least action principle, which tells that the toppling function is actually the minimal function among all these functions which are positive, and this FHP omega is positive, and stabilizing. So that that I highlighted here, phi h plus the Laplacian is less or equal than 3, and that's it. That's immediately we get almost correct upper bound on the toppling function. Does it make sense? So here I didn't. So like I didn't explain one more technicality is that maybe we've chosen wrong the rounding, and this pH is not exactly on the tropical curve, but somewhere nearby. So we would need to perturb a little bit the constant term of the tropical polynomial so that the tropical curve actually passes through pH. But this changes really just by h this bound. So I simply omitted. So I wrote below this that this prime denotes a possible plus minus h change in the constant term, and h is small, so it doesn't really matter for the upper bound. Okay, that was the upper bound. This is an easy part, and guess what? The other side is of the proof is constructing the lower bound. And so this is harder. And this is much harder. So I'm not sure that you'll be able to follow. Tell me when you're lost, and I'll return to the beginning. So ideally, so what will happen is that we will do some partial relaxation for this perturbation state, so for this 3 plus delta at pH. So, and we will try to do it in the very controlled way. So, meaning that in this relaxation, we will try to deal exclusively with those states that we developed in this soliton talk. The solitons in terms of the edges of tropical curves, triads for the smooth vertices, and those deformations of nodes for the cases when we actually have nodes, when we need to pass through the nodes. So the idea will be that we cook up some very specific auxiliary state made only of these solitonic states, and then we will do the partial relaxation with this state. But first we need to prepare for this. So is it clear, the general vision of how it proceeds? So we want to deal exactly with the states for which the model is, so to say, solved. So solitons is the level where we understand everything about how the wave acts, and we will be doing this relaxation in terms of waves. And in a sense, we are doing the estimate of this general state, like 3 plus delta, by the states for which the model is solved. So, okay.
So let me just say something to see if I am, as you said, trying to understand. So you need to find a lower bound. Now you decompose the relaxation process into this series of waves.
Yes.
And then you, for every wave, you can find a lower bound, I guess. But how do you ensure that the final thing is a lower bound?
No. Like what will be happening is that we will be doing only no. So each wave will be within the relaxation. So we will start with some state which is actually smaller than 3 plus delta, and we will be doing waves from this point where we perturb this maximal state. And each time we will be staying below the actual toppling function. So we will be doing only the necessary topplings. Each wave is necessary, but that's a general idea. And but actually, to realize this, we need to first approximate our general convex domain by polygons, by the Q polygons, the polygons with rational slopes of the sides. And this is extremely easy. We just, for every epsilon, we take these level sets of the function f omega. So that's the first thing you do, this omega epsilon. But ideally, we want this polygon to be actually unimodular. But as I told, for not for every domain it is thus. So, for example, if you take a generic polygon which is not Q polygon and go for these epsilon level sets, it will be quite singular, but only with AN singularities. So we actually need to do blow-ups. So we need to subsequently decrease the domain. So we cut the corners in a quite standard way. So we do just sufficient number of blow-ups so that we arrive to this state which is called pi sigma. This one. And this is the polygon, which is unimodular, which is inside omega, which is epsilon close to in the sense of their boundary are epsilon close. So, and what the important property that we established 2 lectures ago was that the curve given by the distance function to this polygon, since it's unimodular, is at most nodal. So this is where this lecture comes. So that
yeah.
Okay, and now we will use this tropical polynomial to construct a state on this pi sigma h, the discretization of the approximation, and this state will be given by the cent-pile approximation. So instead of every edge, you draw a solidon. Instead of every vertex, which is smooth, you put the triad, and wherever you have a node or something close to a node, you use this node approximation kind of solitonic state. Okay, and now actually this is not exactly how we construct it. So this is a vague description of what's going on. I'll tell you in a few slides what we really do, how we really construct it. But this is how you can think of it. So it's some tropical curve which is close to the boundary, which is actually smooth and made of solitons. And so we will be doing relaxation starting with this state. We will never reach the boundary. Our waves will interact only with solitons, and since we know how solitons behave under the wave, we solve the problem. Okay, and so this is what will actually happen. We will prove this lower bound in 2 steps. So first, we note that the toppling function is greater than the toppling function of this solitonic state perturbed at single point. And this I'll be explaining just in the next slide. And again, I already explained, but maybe it will be easier to follow. And then there will be another part when we prove the actual lower bound, which is almost same as the previous upper bound. The upper bound was essentially the same. So it was H-1 renormalization, rescaling of this limiting tropical series. And here we have pretty much the same, but with -3 epsilon. And this will conclude the proof. So if you have these 2 bounds for every epsilon, and there will be and h small enough, h small times h big is between f and f minus 3 minus epsilon. Okay, so that's the global structure. So, and upper bound I already explained, and now I'll be explaining in more details lower bound, and it's decomposed into these 2 inequalities. And the first inequality goes as follows. So that the toppling function of the whole state, like 3 everywhere and 4 at some point, is big or equal to the toppling function of this solitonic state made of solitons perturbed at the same point. So what happens? I want to say that the toppling function of this solitonic state perturbed at one point can be thought of as a partial relaxation for the original state. And there are 2 twists of mindset you need to do to realize this vision. So first, you just imagine that, well, you are working on this smaller domain, but you can think that you are working on the larger domain, but you just never do the topplings outside of this smaller domain. So that's the first twist. And the second twist is that you use the abelian property. So you imagine that you basically start with a smaller state. Recall that solitons, these are actually the loci where you are less than 3. So which means that if you start with the lower state, then you can add up the points afterwards. And so that's essentially the answer to the question. So how we know that doing relaxation for this solitonic state is actually doing the partial relaxation for the original state. So here there are no hidden technicalities. This is completely clear part. Now I think it gets dirtier, and I'll not tell where, but maybe you'll notice. Well, actually, 1 and 2, those are really straightforward. So we decompose this inequality into 3 more inequalities. Or rather, the first one is an inequality and is completely obvious, meaning that the distance function for the level set of this distance function is same up to epsilon with the original distance function. This is completely obvious. Then also kind of obvious, the second, that this limiting toppling function is greater than the limiting toppling function on the bigger set minus epsilon. This is also clear because this is just the influence of these blowups, which are really small. They are actually of epsilon square order. And then comes the last thing, that we prove the actual lower bound, here where it comes from, that the rescaling by h of the toppling function of the solitonic state perturbed at one point is greater than the limiting toppling function on this unimodular approximation of omega minus epsilon. And so you see that you combine the uppermost inequality going from the third, then to second, then to 1. And this is how you accumulate this minus 3 epsilon. And now we are left with really understanding 3. And let's see what I write about that. So explanation of 3. So this state, psi h epsilon, is h discretization of the curve given by this tropical polynomial, which is epsilon close to the boundary, this tropical curve. So it's made of solitons, triads, and node deformations, and we know how they behave under action of waves. Therefore, if we send waves from pH, we know exactly, explicitly, the wave toppling function. And this wave toppling function will be exactly this truncation of the distance function, while also rescaled by h minus 1, which is the step of the lattice. And yeah, that's it. That's the idea. So more explicitly, remember, I was telling that for these solitonic states, if you apply the wave, it means that you change by 1 the coefficient of the tropical polynomial. So this is exactly where it comes from. Okay, and to make it a little bit more precise, here is another thing that comes also handy, that when we send the waves, we deform the tropical curve by increasing the single coefficient, and here we use again this result that our curve stays at most nodal. So we really need to know it in order not to lose the control. And here, okay, I didn't want to explain this during this talk, but it might happen that we lose control, but only if we shrink completely the phase. Remember, the actual theorem was telling that we might have a more severe singularity, but only at the maximal region, the maximality region of those caustic curves. But here, what I say is we just refrain from doing the few last waves, and so that we don't lose any control, and our bound gets a little bit worse because of that, but still it doesn't really matter. So anyway, so the important part here is how we do construct these solitonic states. We do it by smoothings. And here I don't recall what are smoothings, but I hope you kind of remember what this. Just to recall you, the soliton was the stabilization of smoothings of a tropical function with exactly 2 monomials. Right. And here, this is also how we ensure that those solitons are glued properly in the edges, in the vertices. Because actually, when I say, okay, put soliton instead of an edge, you can do that. But then there might be a question, are they glued properly at the vertices? And this is actually how you do this. You don't do it by hand. The gluing, you just apply a sufficient smoothing of the whole thing. Okay? And here is probably where you are. Yeah. I believe you should be completely lost at this point, but if you are not, it's a miracle. I hope you can ask a question. So yeah. So anyway, so that's the end of this proof of this lower bound. And so what actually happened during this partial relaxation? We construct a state which is also still made of solitons, and which is a partial relaxation of the original perturbation state. And also it sits in this epsilon neighborhood of the actual limit, or supposedly limit. So we didn't prove it yet that this is the limit curve. So And also, we know that it's a partial relaxation in this precise sense, that the amount of things to relax is 3 epsilon, at most 3 epsilon. And this implies one side of this convergence by Hausdorff, that the deviation of the relaxation for this original state at one point is somewhere in the 4 epsilon neighborhood of the curve together with the boundary. Okay, and this is one implication about the limit. You need to prove the other way around, that actually, or rather that every point of this tropical curve is realized as some limiting, some accumulation point for the set of deviation loci. And so now this inclusion is true by the following very easy lemma, and this is the last thing I'll tell today, that if you have any state, not necessarily stable, and usually not stable for this lemma, on this omega h, and I think the h should be below, then if you know the bound for the toppling function of this state, then you know that the deviation locus will be somewhere near the deviation locus of the original state together with the boundary. So this is, in a sense, answers your question if we know that theorem C implies theorem A. Yes, but partially, and actually the proof of the theorem, and not the theorem itself. So we really need to know that we construct those upper and lower bounds, which gives us the knowledge that the partial relaxation is not that far away from the complete relaxation, and this says that this implies that the deviation locus will not move too much if we complete the relaxation. So let's prove the lemma and wrap up.
I understand, yeah.
So proof of the lemma, it's very nice, yeah, and you just take some vertex in the deviation locus of the relaxed state, and you assume that it doesn't belong to the deviation locus of the original state together with the boundary. And so since you have that it's not in the deviation locus of the original state, is greater or equal to 3, and since it's in the deviation locus of the psi 0 or the relaxed state, it's less than 3. Therefore, you know that the Laplacian at z is negative, which means that there exists a neighbor z1 such that the value at the neighbor is less than the value at the original vertex. So this is just the consequence of being in the interior, so not near the boundary, and having the negative Laplacian. Okay, that's the inequality 1. So if again this new neighbor doesn't belong to the original deviation locus and the boundary, then we have that again it's Laplacian is non-negative. Here we have no knowledge about z1 belonging or not to the deviation locus of the relaxed state, but we know that in the relaxed state it's less or equal to 3, and at z1 it's maybe, or the original state was greater than 3, maybe it was 3, so it's non-positive. And together with 1, it gives that there exists a second point such that the value at this point of the toppling function is again strictly less. Okay, so if the Laplacian is non-positive and we know that there is a neighbor which is greater, it means that there is a neighbor which is smaller. And so we repeat, and meaning that you have the chain of neighbors, and going from one neighbor to the next, always decreases by 1 the toppling function. And which means that if C is the upper bound on the toppling function, you derive the desired estimate or the deviation locus of the relaxation belongs to the HC neighborhood of the deviation locus of the original state union with the boundary. Okay, so that's it. I think it's very. It's really easy, and it explains a little bit the relation between those theorems. Okay, any questions?
Yeah, it's very nice.
So going in the other direction, like, to be honest. Sorry?
No, you said that it's fine, that it's mostly fine.
Yeah, it's mostly fine. So next time we will be talking about what happens when you throw more points, and purely in the tropical level. So next time there will be no sand piles on the tropical geometry. And then we will make the hybrid of today's talk and the next talk to present the most general convergence theorem we have for the moment for the perturbation of all three states at several points. And yeah, and today we were discussing that maybe there will be a compactification talk like the first and the last, and then it's over. Okay. So I stopped recording.